My name is Costin Iancu. I'm a scientist at Lawrence Berkeley National Lab. And so if you haven't met labs before, we like to run things at scale, and we have a good understanding of system software. So this work has been done with my colleague Khalid Ibrahim and with Nick Chaimov, who sits down here. He used to be our student, and he graduated on Friday, so right now he's our colleague. So congratulations to him. There are two parts to this talk. The first part is I'm going to describe our work trying to port Spark to supercomputers. And the takeaway there is when we started, it would barely run up to 100 cores. When we were done, actually it runs up to tens of thousands of cores. The big difference before this talk and the talk you saw before, which showed you results at very large scale, was I think those experiments were, since they were comparing with the MPI, they were running entirely in memory. So they were never touching except for reading the data, they were probably never touching the storage or the disk during the run. So ours is how you run Spark with large data sets when you actually saw without core algorithms. And as I said, the big takeaway was techniques to make it actually work on our system architectures and scale it very high. After we did this, we were able actually to do comparisons across systems, across HPC supercomputers and data-intensive systems. And there are some lessons there as to what the right machine balance is and what does it take to actually get an efficient system that runs Spark workloads. So we all know Spark, we all like it. It's very good for the commercial domain. A lot of the efforts for its adoption in the HPC domain were sort of not very successful, let's put it this way. One of the reasons was they were trying to port HDFS to whatever the global file system was, and there were efforts from Intel, I think there were efforts from Cray, there were a bunch of papers from Europe. The resulting software wasn't very stable, and the end result was Spark wasn't running very well. There's a lot of incentive in the community. We have huge data sets. You saw the examples, climate, astrophysics. I forgot what the third example was. But they generate petabytes of data, which they need to actually process in real time and generate results. I'm not going to go over what Spark does. For the purposes of this talk is, and if you actually go to HPC conferences, the mantra is data movement is important, and it is important also within the Spark framework. So you have over there at the bottom a cartoon of I think it's a word count, but the point is during the map phases, the data flows between the node and the storage. So this is vertical data movement, and within the reduce phase or the shuffle, data flows both between nodes and to the storage systems. We have both vertical and horizontal data movement. And because of this, the question is what part of the system actually contributes to the performance, is it storage or disk or CPU. So if you look, Spark has been developed for the data center cloud infrastructure. And there's sort of a philosophical difference between that community and the HPC community. In the data centers, you have HDFS that assumes a local storage within each node. It also kind of assumes that all the I/O operations behave equally. When you look how they buy systems, there's a lot of work in optimizing the local I/O for latency. And when they buy the network is actually provisioned for very high bandwidth. On our side, all the installations have a global file system. We know and acknowledge that there's some asymmetry in that file system. There's file metadata, and then there's read-write operations. When you buy disks, I think the procurement put stringent requirements on bandwidth to the backend file system. And also put very stringent requirements on the network for very low latency. So these are two, so if you look, there's sort of a mirror image between the hardware requirements or the hardware design philosophy for the two systems. And one of the questions was whether a software infrastructure developed for the data center, what does it take to run it well on HPC, and whether it runs well at all. So this is a cartoon that shows you sort of the canonical architecture. On the left, you have the data center. You have CPUs, which are either commodity or server grade if you buy a data appliance. You have the memory, which probably these days is the same in both, in both communities. And then the data center, they have local disks, and the network, which is usually InfiniBand these days. On the other hand, the HPC has high-grade components all the way here, including faster networks. And the big difference is we always have a global file system, which is some network-attached storage. And these days, I think most of the installations run Lustre. There are a few that run GPFS, but there'll probably be more. But I think Lustre dominates these days in the HPC centers. And then, so a new fad in design is adding an intermediate storage here, which sits between the global file system and the CPUs. They call it a burst buffer, so it absorbs spikes for I/O. So that's the canonical architecture, and the first part of the talk is going to refer to that canonical architecture. So I'm putting some numbers here. So this is the same Cray system you saw. This new generation Haswells, memory, the network is very fast, and then has a 30 petabyte, I think is a Cray product, Cray Sonexion Lustre global file system, and then it has this intermediate layer called the Cray data warp. There's 2 petabytes and a lot of bandwidth to it. So without further ado, here's a graph that shows you the I/O performance on this two-tier hierarchy. So we are plotting, so where it says Lustre is the global file system, where it says bus buffer is that intermediate storage. We are looking at both file open, which is metadata operations, and then read-write operations. And the data we plot here on the x-axis is the number of nodes, and we plot the average time per operation out of an execution of the group by test. Okay? And the group by is weak scaling. So there's 2 clusters of lines here. So the first cluster here, this is file open, so which is metadata performance. And as you can see, it's not very good at all. So it stops scale. So for example, the global file system stops scaling at 4 nodes, which is 100 cores, and then it blows over there. The intermediate storage scales further. We didn't push it, but you already see the slope here. So it scales further, but not very high. So the whole system has about 2,000 nodes. So right here, this is an indication of a problem, okay? The cluster down here, these read-writes, and they scale well. So we didn't push it to the limit, but I think the system is provisioned to scale relatively well. The big lesson here is when you look at what actually Spark does, for every write, there's a file open, okay? And that's the scalability problem because you have a number of file opens quadratic in the number of cores, and the performance tanks right about here on these file systems. If you delve deeper, this shows you the variability and the mean time for the reads and the file opens. This is a local SSD, and as you can see, there's a mean times the global file system, which is this one, is close to a local SSD. The variability is a lot higher, though. What the biggest problem is here. So the mean time for file open is very low for the workstation. For the global file system is close enough, but it has the mean time is 23 times larger than local disk, but the variability is 3 orders of magnitude. And if you look at the intermediate storage, the variability is only 2 orders of magnitude. So that makes a difference in scalability. So we figured out what the problem was, and then we went and looked at how to improve the performance. And we came up with a slew of solutions. A lot of them are described in that paper, Scaling Spark on HPC System, which appeared in HPDCI, Performance Distributed Computing, in 2015. So the first one is a simple solution. We saw there are too many file opens. We built a cache to ignore the close calls and keep the files open behind your back. This actually improves scalability a lot on the supercomputer, but that's not important for this talk because you have a better solution. What is important is when we move to clouds and the data appliances, which run actually Linux and data center operating systems, we actually saw a lot of performance improvement, which is 10-20% on the end-to-end performance, which is quite high. And the reason was you get rid of a lot of contending file system calls. every single core that makes a file open system call at the same time, and by caching you get rid of it. So this argues for either for moving this maybe even inside Spark, or figuring out a way to use user-level file systems on the computation nodes. The second one is, and this is the one that actually tied it together. We figured out that if we mount the shuffle file system, which is internal to Spark, on a single file, on a single raster file, the whole system software stack will take care of the file opens for us, and it will also give us a lot better data caching. And this was the one that tied it together and actually made it scale. This probably helps also on systems with local SSDs, because probably you get better caching. And actually probably also file opens are also faster. And the third one, which is particular to our environment with the global file system, was using containers, because with the Java I get a lot of DLL opens which bang on the file system, and that limits scalability. All these three address different angles of the performance problems. I think all of them need to be used in conjunction, because, for example, right now we are missing the path of user input data. That needs to be addressed independently, and so on. So, but this combination of techniques benefits both HPC and data center settings. So in terms of scalability, this was the great result. So we plot here, this is the number of cores. So we go up to 10,000 cores. We have three bars here. One is the blue is when you run entirely memory. One is with our mounted file, and then the other one is when we mount the shuffle file system on raster. Okay. So as you can see, with raster directly, oh, sorry. No. What? Stop torturing the animal. Okay, so with raster at 2 nodes, sorry. Oh, this is the, okay, so with raster at 2 nodes already you get a 6x penalty. By 1,000 nodes, we're already getting calls from the sysadmins, and by 2,000 nodes, the system would reboot. So that was a no-no. And then we did our trick, and then we can almost match here the performance when running in memory. So this was a very good result, and actually this enables people to do science and run out of core algorithms on these systems. So the NERSC people, so NERSC is a supercomputing center. They like this idea. They took this and put it in a shifter, which is a container solution for HPC. And I think right now they even decided they like it so much because it helps with Python as well. So they're going to put it in the batch scheduler in Slurm directly. So this idea of mounting a file system is actually turns out to be a very good idea for HPC environments. So now that we did this, now we can actually go and do architectural comparisons. So again, these are the two systems. So this is the data intensive is built by Dell, and Core is our supercomputer. So CPUs are pretty much the same. One has more cores, but the clock speed is pretty much the same. Memory is the same. The big difference is here. So InfiniBand versus the Cray Aries, I think, is a 2x difference. So InfiniBand is probably twice the latency, more than half the bandwidth. But roughly, it's a 2x difference between them. And I already talked about the storage hierarchy there. So the question we were interested in was what is the right machine balance for this kind of workloads. So by the way, the workloads we looked at was spark-perf, which is MLlib, big data benchmark, TPC, and the TeraSort. And if you are familiar with the performance work done with Spark, there was a paper from Kay Osterhout, which is a member, I think, of the original Spark development, or what of AmLab team that was the original Spark developer. And when they looked, their conclusion was that the CPU dominates the execution of Spark, the network not so much, doesn't matter so much, and so you can get 2% improvement if you have the perfect network, and 20% improvement if you have the perfect disk. So in contrast to that, we actually so we ran a much bigger workload, and we also you used the much bigger data sets, and we did weak scaling studies to much higher concurrency. So we ran on Spark 2.02. Actually, I think we ran also on earlier versions. And for the data intensive, we used the Spark RDMA implementation from Ohio University. So the first conclusion is if you do, so this graph shows you the scalability of TeraSort. We run 100 gigabytes per node, so at 20 nodes. At 20 nodes, we have over here, we have 2 terabytes of data. So last third is the global file system. This is the global file system with our tricks. And this is the data analytics, the data appliance. So one node, they kind of match. At higher concurrency, they also match, which is good news for us. And we break down the execution by the percentage of time spent in the application, JVM, so we distinguish also read, write, and so reading the data and opening the files for the data versus the shuffle. And as you can see, I mean, so ours helped here, and then the two systems match in terms of performance. So one lesson we learned from here is, I mean, if you read marketing numbers, they sell you latency and bandwidth. The lesson we learned is variability of whatever that metric is matters a lot more for the end-to-end performance than the marketing numbers. We tried hard to distinguish between network and CPU and disks. The instrumentation is in such a way and it's very hard to distinguish between these two. The only thing we can say here is the data appliance at small scale is slightly faster, but if you actually need to run very high, very large data sets, the supercomputer with the better network actually probably gives you better performance. This gives you a breakdown again of the percentage of time spent in fetching data or the JVM. As you can see across the two systems, the percentages are the same. So this means the machine balance and is similar. The second thing we learned about the storage hierarchy is so for disclosure. Before we did our tricks, putting that layer of intermediate storage inside the system actually helped performance, and it was much higher scalability. Now that we figured out what the bottleneck was and taking it out of the critical path, turns out that you can do as well if you go directly to the backend file system rather than putting that another layer in the middle. So that was the other lesson as far as storage goes. One of the problems is all the transfers, if you look at the transfers that happen in Spark, they are very fine-grained. And intermediate storage probably hides spikes when you have very large transfers. And if you do very large transfers, then yes, it does make sense to put intermediate storage in your system. Then we looked at the network and we were trying to figure out what should you buy, what should you spend your money on, latency or bandwidth. Again, we couldn't get a definitive result because it's a highly oversubscribed concurrent framework, and it's very hard to attribute time where time goes. But empirically, you have three data sets. So where it says Comet Singularity is the data appliance running TCP/IP. This is the data appliance running RDMA, and this is the supercomputer. So the only thing we can say here with some confidence is that you cannot hide 10x differences in latency and bandwidth, but you can hide 2x differences. So if somebody tries to sell you a newer version of a network, which is only by 2x, probably it's not going to offend, probably not going to affect that much the end-to-end time for your workloads. The other lesson was that we looked at when we looked at the network performance is you start seeing the network, the impact of the network when you actually reach large scale. So at small scale here, so over here, so this is about 1,000 cores. You don't see that much impact. Something bad happens here when you reach 2,000 cores and over. So we looked, there are multiple suppositions here. One would be that, so the application driver runs only on one node, and there's a lot of control messages, and maybe the application driver is a bottleneck. Maybe there are algorithms that are not scalable inside the Spark implementation itself. So we are still looking. We are probably going to figure out a cause. In terms of the CPU, our interest was, do you need more cores, and what was the story with the memory? So again, it's a mixed bag. We couldn't make a lot of inferences here. So the only meaningful comparison is when you run the MLlib workload on a configuration using 24 cores and versus 32 cores. At small scale, I mean, the number of cores doesn't seem to matter that much. Only when you get that very large scale, looks like having more cores allows you to better to hide the, whatever, satisfy the bandwidth delay product inside your system. We also looked at a little at KNL. Probably need some tuning, and probably because the way we run Spark, so we don't hit the virtual machine. We just spawn the cluster and then run the application. Probably because that is limited by integer performance. So that remains to be seen how Intel, the KNL line does with Spark. Also, we try to see whether the execution ever hits memory bandwidth limits. Because so KNL has this high memory bandwidth. So you can make, hopefully, we were hoping to make meaningful comparisons between DRAM and MCDRAM. Didn't work that well, and I don't think the execution within these workloads ever hits the memory bandwidth. And those were the architectural implications. In terms of summary, one lesson we learned is, so marketing latency and bandwidth numbers are good, and they provide good information. Probably another metric you should ask for when you buy these systems is the variability. In contrast with some of the previous work and the Chaos-Houts work, turns out if you scale things up highly, you start seeing the impact of the network. And I think the previous talk made the same point. There's a lot of communication in some algorithms. The other conclusion is it runs reasonably well on global storage. So probably you are not married right now to an architecture that has local disks inside each node. And if you're not married to that architecture, that opens a lot of possibilities in terms of redesign, because a global file system now gives you persistence. So you don't need to worry about persistence and failure that much inside the framework. You also get a global namespace. So you can probably think about redesigning how the block manager works, because right now, if you request a block, you go to the owner looks it up, goes to the disk maybe, and replies. With the global file system. Anybody can probably fetch any block, ideally at any given time. And I think that's it. Acknowledgements. The work was partially supported by Intel, which was interested in the global file system. We have this parallel computing center, big data support. And thank you.
All right. Do you have any questions? Right here.
You had mentioned that you had done some testing with Knight's Landing, and you were running into problems because the memory bandwidth was limited. Have you considered trying a GPU with much higher memory bandwidth?
No, I didn't say that the memory bandwidth is limited. I was saying that it has much faster memory. So the Knight's Landing has two types of memory. One is MCDRAM, which is super fast memory, and then the DDR. And I was saying it has much higher bandwidth memory, and I was hoping it can allow us to make inferences about the importance of memory bandwidth on Spark. I was saying the integer throughput is not that great. And we didn't look at GPUs.
So in Spark Summit in February, there was a talk about the scheduling on large-scale clusters. So there seems to a lot of ongoing work on the scheduling part with clusters with many nodes, because there was some sort of bottleneck existing. So do you see any scheduling impact on HPC cluster with like 10,000s of nodes, what's the impact for that?
One culprit was, one suspect was the application driver, the control messages, but I'm not sure that's the case. But I think the previous speaker in the project, in that project, I think in one of their papers, they were saying that they start seeing the resource manager stop scaling at about 50,000 cores or something like that. So I mean, yes, there are a lot of services that I think are spawning only one node right now, which probably when you push it up to tens of thousands of cores, probably it will stop scaling. And I don't know if is the CPU power or the fact that everybody bangs on that, over the network on that resource. So it could be both. But so I think that Mike sits right behind you. I think he can point you to a paper that actually shows you and tells you what it is and where. Okay.
Excellent. One more question?
Is there any problem when Spark runs on clusters but data stored in global storage?
I'm not sure I understand the question. So this is a cluster with...
Yeah. This, you told us
So,
Spark can run on supercomputer. Yeah.
So a supercomputer is a cluster where data lives on global storage. It's just a faster cluster.
But it's not x86 architecture.
Sorry. So the CPUs are Haswell. So the supercomputer we looked at are Haswells, server CPUs, with DDR4 normal memory. The only difference in the supercomputer versus a normal cluster is it has a much better network. Has much lower latency, much higher bandwidth.
Yeah, I
And
get it.
whatever, it's tighter integrated. You can scale it up, but for all purposes, it's a cluster.
Anybody else? One more? All right.
Hi. Thanks. It was nice to see you challenge the Ouster results. I thought they were quite dubious at the time, and it's great to see some academic results coming out about that. My question is related to network. So if network is quite important at large scale, should we be moving to 40 gigabit converged Ethernet if we're not a HPC center and we're not InfiniBand? I mean, Google have gone to that, and most people have gone to 10 gigabit, no oversubscription. What's your take on this?
Probably. So, as I said, the jury's still out. We're still trying to figure out why that bump. And I'm still not convinced that it's a bandwidth problem versus a latency problem. So based on that, I don't know what the latency of the new generation Ethernet is. If it's not that good, I don't know. I mean, so I think we still need to figure out if it's a latency or bandwidth problem. And for sure, there are problems where it's a bandwidth problem. I mean, there are application domains where it's a bandwidth problem. But more than that.
All right, looks like we have time for one last question over here.
Thanks for that talk. It was really great. Lots of good information. I was kind of curious. It kind of like slid by really quickly that you said when you containerize things, you got a 20% speed up.
Yes.
Do you have any comments as to how that happens?
Yes. So when you run at scale, the JVM does a lot of DLL opens, and all of them bang on the file system. So that is a particular phenomenon that happens only on global file systems. If you have local disks, probably it doesn't matter that much. And besides Java, Python has the same. So in HPC, whenever you run Python applications that use Python, it's a common problem, and everybody acknowledges it and takes care. So this trick takes care of that as well. So that's why they like this idea of mounting. And yes, sorry. Okay.
All right, let's give our speaker one more round of applause.
Thank you.